Okay, hi everybody. It's a pleasure to receive today Alan Anderson Pereira. Alan is now working at Universidade Federal de Alagoas in Maceió. He had his PhD at IMPA in 2018 under the supervision of Roberto Imbuzeiro, and is mainly interested in discrete mathematics and probability theory. He also had a small postdoc stay at UFMG, Universidade Federal de Minas Gerais, and now he will speak about the Chinese restaurant and concentration, more precisely concentration inequalities for this model. So it's thank you very much for accepting the invitation. And Alan, the floor is yours.
Thank you, Sandro. I'm very happy by the invitation. Thank you very much. It's a pleasure to be here. And my English is a little enferrujado. I don't know how to say enferrujado in English, as you can see. Rusty. But I hope it can be fluently done. I will put my window here. Okay. My screen. So, thank you again for the invitation. And I will talk about the generalized Chinese restaurant process. This is a random partition model. And I will start by in a very simple way, so we can grow and increase the abstraction until we start the real model, the main model. First of all, let us remember what is a partition. A partition of a set is a family of subsets. We take A and literally we split in parts, okay? So P, the partition, is a family of subsets of A. This means that the union has to be the A1 until A2, AN is A, and the intersection of each part has to be empty, okay? So we call this number the quantity, the number of members in the partition of number of the partition is literal. Exactly what it means, what it has to mean. And a random partition is a partition that is taken randomly. To familiarize with that, we can think about a partition defined by a family of Bernoulli's random variable. We take a Bernoulli random variable with index 1, index 2, index n, and we make the choice randomly if it can be 1 or 0. If it's 1, we can put in the first set, in a set A1. And if it's 0, we put the index in the set A2. So in this way, you can partition the set 1, 2, 3 until n in two subsets. In the subsets A1 and the subsets A2, and they are random. A1 is a random set, A2 is a random set. In the future, we want to give another more abstracted partition of this set, but the idea can be summarized here. Okay, if anyone wants to ask anything in the middle of the presentation, is invited. Okay, so here we partitioned the set 1, 2 until n in two parts. Here n is fixed, but we can change the n. We can take n equals to 1, equals 2, equals 3, and go on. So we can say that we can partition the sequence of sets. We can partition this first set by this way, by Bernoulli's, for example. We can partition also the second set, 1, 2, by Bernoulli's. We can partition the set 1 through 3 by Bernoulli's. So we have a dynamic partition, because in each time we have a partition different, made on a different set, okay? And this is we can say, the main idea inside the model we will talk about in the next 3 pages. Let us see the model in the case, in the more human version, without mathematics yet. First, in each time, a customer will enter in a giant restaurant. The restaurant has infinite tables, so the people can sit everywhere they want, every place they want. And the customer will choose a table and sit. The customer enters, in each time one customer only, and he enters and choose a table and sit. But the customer is polite and he doesn't sit in the table, sit in the chair. But we will say by simplicity of communication that he sits on the table. And the customer can choose this, or a table that is already occupied, or he takes a new table. Then the table is not labeled, so we will label the table for the time that the order the people occupy it, okay? The table has no previous label, but we label always that it's occupied in the first time. And the labeling is like that. If we have K table occupied and the people and the customer take a new table, we label it with the number K plus 1. So this is the model. This is the part heuristic of the model. And what we have to define formally now is how is the decision of the customer. How the customer will choose a new table or a occupied table. And about this model, there are 2 types of questions that we worked in this work, that we wasn't interested in this work, is a common question about this type of model. And the first one is how many tables are occupied in this model. This question was answered in a asymptotic way before, and this work is about the concentration of the number of tables, okay? So for representing it mathematically, we can put Vn as the number of tables, the random variable that counts the number of tables. And we have another question that is how many tables with K customers are that there are in the model, there are in each time. These questions has let's say a marked appeal too, because we can use the random partition, for example, to study as a toy model, in fact, of the market, because we can think about how many customers some empresa. Sorry, my English failed here. How many customers a company have, or how many companies about in some some type of market there are in the world, for example. So Vn can represent this quantity of companies, and Nk can represent the how many companies is of each size. Okay, how many small companies or how many blue caps there is in the world, in the stock market still, and so
Alan,
on.
just to be sure, at this
Yes?
level, Vn, we can see Vn as a non-decreasing process, increasing
Yes.
by one unity at random times.
Yes.
Something like that. Okay.
Exactly.
Okay. Keeping at the same value and then increasing by one and so on.
Mm-hmm.
Okay.
Exactly. And it's also, and in fact, it can be not. It varies by one also, but it can increase or decrease because if some people enters in a table, and this table has
okay.
people, okay, and the work, in fact, the paper where it is based, consider that these two questions, these two random variable, but here we will talk about the first one. The idea of the two model, the second one, is similar, but there are some lines that is different. Okay. So now let's talk. I see now that I used the wrong version of the PDF. Okay, but the customer decision will be made, as said, it will be made randomly, and we will follow two variables, two parameters. The first one is about the decision, is because the decision is based on the number of people in a table. If we think about a table, it can be counterintuitive that the people will sit in the table where there are many people. But if we think about the market model, not market model, but the company thinking, let's say, it's natural that people become a customer of a company if this company have many customers, have so many customers, because people like has more confidence in company that has many customers. Because if you are the first customer of a company, we can think, oh, maybe it's not a good service, maybe it's not a good product. So it's this modeling makes sense in this if you think in this way. And the other parameter you consider is that people okay, is that people will want the table in our consideration where there are many people, but people want to also look at the possibilities, so they can choose a table where there is no one. And this model where people want to go for the place where there are many people is called preferential attachment. Is very, very useful in graph theory, and is called also of rich get richer, because we can think about the people who has so much money, they can invest and make more money. If you doesn't have so much money, we have to pay your bills, and so you cannot increase your wealthy, healthy, bom, riqueza. Okay, let's see the model now with numbers, with mathematics. The Chinese restaurant model will be a dynamic random partition. So we will take a sequence of sets, and in each time we want to partition the nth set, okay? The set n. We have the set 1, the set 2, the set 3. So in time 1, we want to partition set 1. In time 2, we want to partition set 2. But we will have a consistency in the partitions. First, we have the parameter alpha that look to the measure of interest in a new table or in a new company. And you have a parameter theta that measures the trend of diversification. Okay? Okay, is that? So let's give the model in fact. The Chinese restaurant model will be the sequence of partitions. So partition 1 is about set with the number 1, partition 2 about set 1, 2, and so on. And each partition is determined.
I think it will be clearer later, but when you say alpha parameter that measures interest in a new table, does it mean that it's like the larger is alpha, the larger is interest in taking a non-occupied table, or it means, I mean, it's just some, it does not have some, I would say, the larger is alpha, the larger is the one, because diversifications to me, the second, the theta, it seems to me that it would quantify how much people want to go to other tables. But is it something intuitive like that, or?
Okay, I think it can be better said these points in this way. Alpha is about taking a table that's not occupied, and theta is about we doesn't concentrate in a table because we are in a Pereira attachment. But here, this theta will help to people doesn't take every time the same big table. Okay, this makes sense. Does it make sense?
You mean theta helps people wanting to go to big tables? This is what you said?
No. It helps to doesn't go to necessarily to big tables. Mm-hmm. Okay. So I will think about how to write it better because in fact it's very confused. It looks like it's the same thing.
No, I think the formula will be clear when you will give us the formula of the distribution. It will be clear. But now I was confused.
Okay. So in the first set we have only one subset, not empty subset is himself. So the first partition has to be the partition that contains only the set in the whole set. But now we will how do you go from time n to time n plus 1? Suppose that we have k tables occupied. K tables occupied means that the partition times n in time n is the first table, the second table, until the kth table. So we have a partition in k subsets, and now we want to choose the customer enters in the restaurant, and he has to choose a table to sit. The probability he takes the table J is the number of people in the table J minus alpha over n plus theta. If we put a big theta, in the beginning, these numbers will be well distributed. But if theta is small, in the beginning, the tendency is to go to table that are big in the beginning. So it's in this sense. Okay, Sandro? In this sense that theta
Okay, so you mean in the beginning?
Diversification.
Okay. Mm-hmm. Okay.
And the
Hi, Alan. Can I make a short question?
Appear.
Just to be sure, are you going to are you present the generalized version of the Chinese restaurant process, or is the basic one? It's a new version of the process, or not? This slide is already okay.
Okay. So, and to complete the probability, to be choose the sum of the probabilities becomes 1, and we can have new tables. We can put the probability of choose a table times the number of tables plus theta over n plus theta. Okay, this is we can say the important part, because this part in the probability represents the tendency to occupy new tables. The theta is only to the sum becomes 1. Okay, so this is the model. Somebody has any question about the model? Okay.
A question about the range of the parameters alpha and theta. In theta is positive and alpha is positive also.
Alpha is positive, and theta has to be bigger than minus alpha.
Okay.
Okay. Because
only one more question.
If positive, and it has
if I
to
want
become. Okay.
Sorry. The basic model, the basic Chinese can be recovered if you take, for example, theta equals 0 or not. Oh. I'm trying to see how can I obtain the basic Chinese restaurant process. Is it an additional parameter that is the generalization? Is that the thing? Or not?
In fact, I don't remember the basic Chinese restaurant process.
Okay, no problem. No.
So
no problem.
Okay.
So I'm also trying to remember. Don't.
Okay.
No. Okay, that's okay. No problem.
Ernesto.
Sure.
Just one comment. Are you not confounding with Dirichlet process?
No.
Because Dirichlet process has just one parameter, that's alpha.
No, because no. What I'm asking is that what he's present is a generalized Chinese restaurant process, and we have a basic one.
Okay, there is another version.
Yeah, maybe the usual Chinese restaurant process. That I don't remember if there's two parameters or only one, the basic one.
Okay.
I think also it's only one, no? I also.
I'm not sure. I just know that Dirichlet process just have the alpha.
Yeah,
but the Chinese version, I don't know.
I think the Chinese restaurant process is how can I say, is obtained from the Dirichlet process.
Okay, then in this case it has just the alpha.
Yeah, I think so.
Just the alpha.
I'm a little bit forgetting about this. Okay, no problem. Go on.
Okay. So it's was known before that this quantity, the number of tables, converges, and is also known the limit. It converges when we normalize it by a constant. So it converges to a random variable that is relatively well known because we know the density of that, but it's very complicated density, and I think it cannot be done anything with that. But we know about convergence, and we know about convergence when we vary the parameters for alpha constant to equals to 0, for example. It leads to a model that will be fixed because we don't want to put new tables. If you take a partition, not the partition, but the initial set relatively big, we know what happens when theta is equals to minus alpha. So there are many results about this, the convergence of this model. And the work, in fact, is about the concentration of this quantity around this limit that was well known before, okay? And the results that, I think someone talked in chat. Yes, okay, legal. Okay, so the result is about concentration of the sequence of random variable that converge to the limit of the number of tables. So many of in the sentence. And the concentration result says that for all random variables, all times, the normalized number of tables is near of the limit. Okay? And
the limit itself is a random variable.
The limit is a random variable, yes. And we know that in all time, the same time, how let's say it better. For all random variables, for all m, the probability of everybody happens in the same time, everybody be near to the limit, is near to 1. Okay? Doesn't it make sense?
You mean that you are saying that this is a probability that at each time n you have been close to the random. It's not for any m that you have this inequality. The probability is high. It's for every m that you have this.
It's for every m.
Okay, so it's like an intersection of events, of infinitely many events.
The intersection of all that is big.
Okay.
And this is I think the interesting part of this result, because it's not a concentration, an asymptotic concentration, and it's not asymptotic. The asymptotic is the limit, so we had to do some step after. So the good part is that we doesn't have a asymptotic concentration. We have a simultaneous concentration, let's say. And the concentration, the approximation has order given by the theta, the parameter, the first parameter, and the alpha, that is the other parameter of the model, okay? And as much as you want to guarantee this result, or the error of the probability, we can control this by another part here. So if you want to if you want that the probability will be 90%, we can do that, but we lose a little of we lose the approximation a little. It's not so significant. So the influence of the delta is not so big because we have a power of m here. So it's a useful parameter here. Okay. Any questions? Okay. Our next step will be to see how we can prove that. What's the idea to prove that? So I tried to reduce the abstraction, looking through theta fixed and alpha fixed, but the idea is similar if you want to take other theta or other alpha, and the difference will be like a problem of real analysis in the other case. It's only look to other series that will appear here. Okay, so the idea is we want to concentrate Vm over Phi.
Sorry, I'm not sure if you said what is Phi-m. What is the scaling parameter? Did you mention what? It's too complicated to be written.
No, it's not. It's only we will see here the parameter, but is something like a gamma function of m theta. Okay.
Okay.
It's like a m factorial. Let's say is a ugly version of m factorial. Okay.
Okay.
Okay. So what we can do here, as Sandro observed before, when we vary the number, the size of the table, we only can vary it by 1 or 0, because in each time, or we have a new customer, or the number of customers stay constant. So this random variable, this variation, is a Bernoulli random variable, and we know the parameter of this Bernoulli depending on the number of customers in the table, because the probability that a new customer take a unoccupied table is alpha, 1/2 here, plus theta over m. So we know exactly the parameter of our Bernoulli, but it's a conditional parameter. So we have a conditional expectation here. Okay. And we can do the calculation, the simple calculation. We write Vn as Vn minus 1 plus the variation. We just substitute. We make a substitution of the delta, and we operate the numbers. So we can write Vn, the number of customers in the table, as a function of the number of customers in the table in the last time, plus a random variable that is Bernoulli minus its parameter, so is a centralized Bernoulli, we can say, plus a thing that we can control in some sense. So we only have to make calculation with this arithmetic geometric sequence, okay? And here is where the parameter phi n appears, because we can take phi n exactly to control this arithmetic geometric sequence. We can take phi n as the product of term like that, in such a way that when we divide the expression by phi n, we take a more sympathetic sequence, because here we have Vn over phi n. Here we have the analogous in time in one time before. Here we stay with centralized Bernoulli, but we have now a constant, a parameter, a normalizator that will converge in some sense. Okay, and here we have also something that converges, so we can control that easily because it's n times something bigger than a power of n, so it converges by real analysis. This part is intimately related with this part, and that is the sequence that converges. Okay, and this part is a centralized Bernoulli. So if you don't have so much familiarity with this thing, we can. If you have if you know what that, we are constructing a martingale here. If you don't know what's the martingale, you can think that we have in each time like a fair play. We have a game where we have the same chance of win and lose. So the expected number of the value here will be 0. Okay, this is what we call essentially a martingale. So what we can do here, we can take this, let's see, here is just what we are doing. Okay, this doesn't say anything. What I want to do here, we have Vn, so we can change the value of n, interact the expression, so we can change Vn to a bigger number Vm, and from m to n. Okay, essentially. Okay, my English and my mathematics, they are working against me. What I'm trying to say is we can interact this many times, so we can choose the point where we start, and you can choose the point where we finish by this equation. When we do that, we will sum many times this, and we will sum many times this. When we sum this part in the middle, we will take a martingale or a difference of martingales that is martingale also. And when we sum this part, it will converge because this has order bigger than n in the below part, in part below. Summarizing, we have this expression. Here we have Vn as function of a time before, plus a martingale, plus a numeric part that converges. When we send it to infinite, Vn will converge to V star. Vn over phi, in fact, not Vn, but Vn over phi will converge to V star. This part we want to stay fixed, and this part, no, this part is only real analysis because converges is a numerical part. And the martingale part, we can prove that converges by martingale results about concentration. In being specific, we use here the Friedman inequality. It's like a Zuma-Hefting inequality, but for quadratic martingales, quadratic integrable martingales. Okay, and that is this. When I translated I forgot the reference. Sorry, and thank you for the attention.
Okay. Okay. Thank you, Alan. Thank you for the talk.
Alan, let me see the last slide before the obrigado, please.
Okay.
So we are open to questions, suggestions, and observations. Renato.
So once you control the martingale, then you get the result that on Vn on V star. That's what happens.
Yes, we control the martingale part, but we control very well because the error will be so small that we can intersect the sets and the simultaneous result will occur. Okay, is this answer?
It's okay.
Okay.
But is it possible to get another? Do you know if it's possible to get another results on this process with the martingale theory?
Another. In fact, for this process, I don't know. I don't know because in fact the result using martingale, the other results done about the generalized Chinese restaurant process that are in a Pittman book, they are not by martingale theory. So I don't know. There are other results about medium deviation. It's large deviation, but without other scales. But they are not also using martingale. So using martingale, I only know that. Maybe there are others, but I not so actualizado about this model nowadays. But
Updated.
Updated, yes. Okay.
Okay, thank you.
Thank you.
Okay, is there any? Yeah, I think Andressa wants to speak. Andressa, please.
Thank you, Alan. I have a question about this V star, because in the proof I can see that V star comes from the convergence of Vn divided by Phi. So here's where V star appears. That is the same V star in the statement of your theorems, right? Can you say a few words about this random, because this is a random variable. I think you said something about that. So can you say a few words about how it looks like, or?
This is the point. It's known exactly. This is a continuous random variable. Okay. The density is known. It's not very simple. It depends on gamma function, and this is given implicitly using gamma function.
Okay, so you have it explicitly. So you have the density of this random variable. That's cool.
It's known, and I think it's that about the density.
Okay, right.
And,
okay, thank you.
Thank you for the question. Any question more?
Any other question? Alan, let me ask you, when is it, because usually concentration inequalities, you say like, so perhaps so in this case, you know that you have an almost sure convergence to V star. So my first question is, now you have concentration inequalities, which is very strong, which is that it's like the probability that for all time long, forever, I will be close to V star at a certain distance, but close. you can say that it's bounded somehow. This is, I mean, so usually the concentration inequalities, they are given for fixed m. So you look at, for instance, if you look for the sum of random variables, you will say, okay, I mean, the classical concentration inequalities would be, what is the probability that your sum until n be close to the mean, say, the rescaled sum, so say by n, in the very simple context. And you say, what's the probability that up to n, we will be close to the mean. And then you say you have something like exponential probability depending on n and so on. In this case, this is automatically implied by your result here, this kind of inequality for each n.
Yes.
It makes no sense. Okay, so your result is strictly stronger, and you can get this kind of results also.
Sorry, I didn't understand this.
No. Can you get this kind of result from your result, which says that at every n until forever we have this process to be closed?
Okay. And I will answer, and maybe if I am not answer the question you said, you stop me and I try to redirect. If I understand the question, is about because here we have in all time, but if you want to look only to a fixed time, is about that you are asking? If it happens from the result?
Something like that. So just because I was not used to this kind of concentration inequalities you are given here.
Okay. I think that the answer is, in fact, we prove the result to fixed m, and the inequality, the concentration is good enough to we can take the intersection of everybody, and it happens yet for simultaneously. But the point is that in fact we prove the usual concentration only to a fixed m, because we prove to m, this n goes to v star. So essentially we are giving concentration to vm only, and by adjusting the variables we can join the other values of m. We can vary the value of m. Okay,
Understood. Okay, thank you very much. Is there any question, and is other question or observation? Otherwise, I'm not sure, Michel, what is now the procedure. We say one more time, we say thank you very much to Alain. What?
Yes.
What? Okay, so one more time, thank you very much, Alain, for having accepted the invitation and for this very nice talk. And that's it. So see you and everybody to the next seminary. Michel, what will be the next seminary? Do you know? Do we know now already?
I'm not sure right now. I can send a message later.
Okay. Well, so that's it, Alain. Muito